from far away. I'm from Denmark, up north in Scandinavia and Europe. So I'm a little bit jet lagged, but fun to be here. I'm going to start out with a little story because I'm a little older than I look. I have a 16-year-old daughter, and every year around Christmas time, she has a story that we talk about every year, and something that lights up in her eyes. And it's about me and her building a snow hut. That one Christmas in Scandinavia where I live in Copenhagen, where there was actually enough snow to sort of build anything of a decent size. So you only have that one chance. I've done it many times during my childhood, and I've had a lot of fun doing it. There's no doubt that climate change is here. I guess you're here in this session because you believe in it too, and you want to know how you sort of can have your impact, how you can help Mother Earth. I'm going to walk you through a journey of a project I did with a company in Europe where we built a green supercomputer. I'm going to talk you through the challenges we met, the solutions we built, the outcome, the impact, and show you some tools so you sort of can replicate the same things. Please do ask questions if you have any. Raise your hand or anything like that if it's not clear or anything you want me to specify even further. The more active a session we can get, the better. So I'll move over here a little bit, one of the sides. So the company is Vestas, and Vestas is the world's largest wind turbine manufacturer in the world. And they're also the most sustainable energy company in the world at the same time. So they contracted us to design a solution to simulate these turbines. These turbines are huge. So the one here is, for instance, is a V236. It's just the name of the model of the turbine. The 236 actually means that the length of the blades is 236 meters. The tower is normally around 150 meters tall, and the nacelle, meaning the house where the generator and gearbox is and stuff like that, weighs 880 tons. So I was actually on site seeing one of these. It's the largest turbine in the world when they lift up that 880 tons up to 150 meters up in the air. But these turbines are, first of all, they're huge. They're massive, but they're also extremely complex. So the tip of that turbine blade, which is at that end, travels faster than any race car. It has to do that for 30 plus years. That's the maintenance period for a turbine. Actually, a fun story. When I was at the R&D center in Porto, in Portugal, I asked the question, why not, when you see smaller turbines, you see them spinning quite fast. This doesn't. There's a max of RPMs of 15, because if they go above 15, the tip is going to break through the sound barrier. That's how big they are. Each of these turbines produces enough electricity to power 20,000 homes. So they're big. They're extremely big. And we needed to simulate these turbines before they were actually erected. And some of the simulations we did was load simulations. Like when you have this huge turbine and a wind gust comes towards it, what kind of torque should you have on the bolts, or the thickness of the walls in the tower and stuff like that? Optimal placements when they are in a wind turbine farm, so they don't block for each other as little as possible. And we did all that via simulations. And there's a huge difference between if you take a turbine and you put it somewhere inland in Australia, for instance, or near the coast. There are no wind gusts inland compared to the coast. So the difference in material use could easily be 50 tons, just 50 tons of steel less. You don't need that much. So each turbine is purposely built for that location where it's supposed to be erected. Vestas had already an on-premise supercomputer, not a huge one. It was always struggling keeping up with all these simulations they needed to do, but they were looking at a new solution that was green and could scale to enormous size. So they wanted to be able to scale to 400,000 cores, which is a lot. So they'll be able to at least run 400,000 processes at the same time. They wanted cheaper than what they already had or what they could buy on premise. And they wanted it as green as possible. They actually chose Microsoft. I work for Microsoft, by the way, as the provider, as we had some of the tools for it, but we didn't have all of it. So we sort of had to build and doing while we did this. And an interesting fact about carbon emissions is that our industry, the IT industry, actually emits more carbon than the aviation industry. That's quite interesting because all we talk about is you're supposed to fly less, perhaps you eat a little bit less meat, red meat at least. But in fact, we almost emit twice as much, our industry. So that's a lot of carbon emitted into the atmosphere. And I hope you're thinking, what can I do as a software engineer right now? Because that's what I'm going to talk about. So there's a foundation called Green Software Foundation. They work around green software. It's a lot of companies, including Microsoft, actually contribute to the Green Software Foundation. And they have built a number of principles. They actually have 7 or 8 principles. I can't remember all of them. But they're sort of grouped into these 3 categories. So, sort of energy efficientness. Like, how do you make your program more energy efficient? Of course, you can write better, faster code or whatever you want to. You can also choose a different programming language. And I've added this one just for fun before I show you anything here. There's a PhD student a couple of years ago that created this comparison of languages, which one was most time intensive, used most memory, and the most energy. And I keep pointing that one out because I have a lot of friends that really likes Python. So I thought, don't use Python. That's actually not my point here is, of course you should use Python. You should be using the tools that sort of make sense for you, right? You should optimize for developers first, then deployment. Like, I bet most of your code does not run on 400,000 cores. Yeah, you have a question?
Regarding the hardware.
Yeah?
Facebook many years ago went to the open hardware.
Yeah.
Initiative with servers for data centers. So Microsoft has something similar?
So the question is, Facebook has open hardware initiatives about how you design those systems, whether or not Microsoft has the same. Yes, that's actually not because we wanted to make it, as far as I understand, make it available. It's about having a lot more suppliers building the same solution. I don't know any details about that, so I can't really, I just do know that all the specs of how we design our data centers and stuff like that, and even the server racks and stuff is public available. So optimize for developers, optimize for delivery, and most of your code won't run on so many processors. It doesn't really matter which of the programming languages you use. You should pick the one that sort of suits you and your solution. Then there is hardware efficiency. Right size virtual machine. Pick the right size if you're running on a virtual machine, of course, but it doesn't really matter. Whatever you pick, you have to pick a size. It shouldn't be too big because it's just idling and consuming resources. Azure, again, sorry, I keep mentioning Azure because that's where I work, that's what I know, has Azure Advisor will actually tell you, if you go into the advisor, which nobody does, saying, your VM has never been utilized more than 12%, pick a smaller one. You can probably also use a Copilot for that. Then there is more efficient processors. Like, this solution was written in .NET, and .NET can compile to ARM. ARM processors are way, way, way more efficient than x86 or x64 because they have all the backwards compatibility. You can see it on your phone. It's over there. The battery lasts a lot longer on your phone than it does on my laptop. Even though my laptop is doing nothing. I don't even have to have the screen on, it'll last a lot longer. So you can choose a different CPU architecture. And of course, turn off unused resources. Like, you can't turn off your corporate website, but I don't know, your HR system could probably turn off during night and weekends and stuff like that. And then there is carbon optimization, carbon awareness, sorry. And that's where I'm going to drill quite a bit deeper into. And carbon awareness is about when are you supposed to compute and where can you compute. But I'll get deeper into that one first. But first I want to share a little bit more about energy efficiency and hardware efficiency. I don't know how many of you knows PUE. When I'm around presenting, people talk, why do Microsoft not share the PUE for data centers? We sort of do, but not really, because we're afraid of how people use it. We know the PUE of all data centers, and the PUE is power usage effectiveness, is about whatever amount of electricity you draw from the grid. In this example, 15 kilowatt. Some of it goes to cooling, which has no value whatsoever, and the rest goes to the compute power that you actually need. So you're basically wasting, in this case, 5 kilowatt out of the 15. And in this case, the PUE is 1.5. Data centers around the world, 10 years ago, the PUE was above 2. Now, regular data centers are around 1.5, 1.8, new ones. Hyperscale cloud, not only Microsoft, is around 1.12, 1.15 or so. So they're becoming really, really efficient. And then you got to remember these hyperscale data centers work on scale. So if we can cut off 1% waste of energy, Microsoft is going to save millions of dollars a month. So they really try to do a lot here. But the PUE is really difficult just to compare, right? If you have a data center running in here, or actually a better example, I have no clue how, in Norway or something like that, where it's cold all the time. You don't need much cooling. You just open the door and then the server is cold or freezing, probably a little bit heaty. But if you move the data center to Singapore, where it's humid, wet, warm all the time, you need a lot of cooling. So you can't just compare data centers saying, okay, the Norwegian one is really efficient. Like the PUE is around 1, but in Singapore it's 1.5 or whatever the value is. That's actually why we're not sharing it, and nobody else is sort of sharing it. You can, it's not public, you can get it if you ask for it, but only on the specific Azure regions you want to use. All right, so before we dive down to the carbon awareness, there are a couple of things we need to do. That's just is common sense, but you need to do that if you're doing things at scale. So the most power hungry, what requires most energy in a data center is CPUs. And it's also the most costly resource. So we wanted to saturate the CPUs running at 99.9 or 100% utilization, which we of course can't reach. So we needed to figure out how do we do that. We made sure that none of the processes more or less never waited for I/O, for instance. So we saturated the CPU as much as we could, meaning we shouldn't pick too large a CPU to compare to the workload we were supposed to run. And that tried to indicate here with a piggy bank here that we saved a lot of money by utilizing, and we also saved a lot of carbon by making sure that we didn't waste any resources. We right-sized the VM. We actually ran the workloads on different virtual machines with different chipsets and all that stuff, and figured out which one was the most efficient at this workload. And there was a huge difference. I was surprised by that. So depending on what workload you need to run, you can run different virtual machines. Our cluster should be able to scale up to 400,000 cores, but we also want to be able to scale down. So their workloads is sort of over a year changes. So in some periods, nobody buys a turbine, so they have no calculation. So the cluster is close to, or actually the cluster has 0 cores or 0 VMs or anything like that. So it costs almost nothing to operate, doesn't emit any carbon. But of course, we had an API or a front end. That's so we always ran at least one virtual machine or one server, so we can sort of address the API, and then it would start spinning up clusters and all that stuff. And then we utilized existing resources that was already there. So at all the cloud providers, you can actually reserve instances or prepay for a number of instances, which is allocated to you. So Microsoft, in this case, guarantees that if Telstra wants 10,000 VMs of this type, they will Microsoft will make sure that there are always 10,000 instances available in that region that they want it. But if nobody's using it, they're just sitting there idle. They are produced, manufactured, shipped, whatever. So we actually enable others to use those. We call them spot instances for a heavily discounted price, 70, 80, 90% discount of what we already did. So that saved a lot of money, and of course also a lot of carbon emissions for not producing additional 10,000 virtual machines. The only downside here is that you can be evicted. So if Telstra wants their 10,000 machines now, you got 30 seconds to shut down whatever you got running, otherwise they'll just disappear under you. That was something you need to solve. So
just on that, we have part of the work we do, we have quite a lot of build processes that run almost all the time online, and we use what is all the time to have qualified. We'll quite happily kick off the night and build the service straight away.
yeah.
That's the way to get them at a short amount of time. The spot is absolute saving for us.
They have. So mentioning that you had a lot of brew process or cron jobs or whatever it is running in the background, and then spot instances work really well. And a little secret, they don't get evicted very often. so yeah, it's very, very seldom. You can actually see how often each SKU, VM type, gets evicted in each region, and the numbers are really, really low. Yeah. So that's a very efficient way of running your workload. So I've seen a lot of customers actually running dev clusters on. I'm not sure I would do that, but you can run a Kubernetes cluster on just spot instances if you want to. Cool. Carbon awareness, right? This is a big thing. The other things is done before, it makes sense financially and all that stuff. But carbon awareness was the new thing we sort of brought to this solution. And when we talk about carbon awareness, we need to sort of talk about carbon or carbon dioxide, right? This is the formula for carbon dioxide. But carbon dioxide is not just carbon dioxide or carbon. You keep using the word carbon, but we actually mean carbon dioxide equivalents. And this is the formula for carbon dioxide equivalents. And it's a measure used to compare the emissions from various greenhouse gases based on their global warming potential. So, for instance, the global warming potential for methane, is that how you said methane? Methane, yeah, something like that, is 25. And for nitrous oxides is 298. Meaning methane is 25 times more potent greenhouse gas compared to carbon dioxide. And of course, nitrous oxide is 298 times more potent. So everything is just calculated into the equivalence of carbon, so hence the carbon equivalence. We also need to talk about something called carbon intensity. And carbon intensity is how you produce electricity. So it's about the number of carbon equivalents emitted to produce 1 kilowatt hour of electricity. And it depends on, of course, your energy source. So if you, for instance, and how your grid is sort of built up. Down here in Australia, I know there's a lot of coal. There are other places also. In Denmark, we have, funny enough, a lot of wind turbines because it's always windy and cold and wet. But the electricity mix is how the world is sort of, let's say, running. And if you look at the electricity mix worldwide right now, until at least 20, you can see we mostly use coal, but that curve is actually breaking off, and you can see the renewables going up. That we have more and more renewables, and it's even going further up the last couple of years. I just couldn't find proper source with more recent data. And nuclear is sort of still at the same point, which is a good story, except that our electricity requirement has doubled many times over the last 20 years or so. And you can see coal is a huge part of that right now, and it still is. And our transition into EVs and other electrifying the production, it requires 2 or 3 times more electricity in the next 10 years than we are producing right now. And if we don't do anything about it, it's going to be coal and gas and stuff like that. Perhaps a little bit nuclear, if they ever finish a nuclear plant. Cool. So time shifting. So why would you want to do time shifting, right? So this is, sorry for my terrible handwriting, but you sort of get the point here. If you look at it over here, we have 120 grams of CO2 per kilowatt hour. That's this carbon intensity. If we look at a point of time, you can see this is produced with coal, gas, and a lot more wind and a lot more solar. But later in a day, if you move over to the right, if the sun sets a little bit or the wind stops, and you still have the same demand, you have to fill that demand somehow, and that's why you start your coal plant or increase the gas production to be able to meet the same requirement. And then suddenly your carbon intensity go up to 350, for instance. And if you put that in a curve over the day, this is sort of like it would look like in many countries where you have a lot of solar power. In the morning, you won't really, it's mostly gas or hydro, whatever you produce, and then a lot of solar power. And then later in the evening, when people start cooking and stuff like that, and there's not a lot solar, you'll see the curve like this. So if you can move your workload from this point and move it 1.5 hours or 1 hour and 23 minutes in, you can actually lower the carbon intensity of your workload, right? And if you know how long this workload takes, which we did in our case, sort of, at least, we could sort of figure out, okay, cool, you just submitted a job. Do you need it now? We actually asked the user, do you need it now, or can you wait until tomorrow morning at 8? We'll make sure it's ready for you. And then we asked the system, and that's why I'm going to talk a little bit about, okay, cool, when is the ideal time to process this 1 hour workload, for instance? That's super simple. That's actually fairly simple to do. And we use some data to how to get this carbon intensity, and we use a tool called electricity map. There are others, there's WattTime and others where you can get this kind of information. This is a snapshot in time, about a year old, you can see, of Europe. And I deliberately picked the Netherlands and Sweden Central because Microsoft has 2 regions there. The biggest one we have is in the Netherlands called West Europe, and there's one in Sweden Central that's called Sweden Central. And fun fact, where is Europe North? If this is Sweden Central, anybody know where Europe North is? It's in Dublin. Doesn't make sense, but that's the other actual reason. No, but the point here is you can see the carbon intensity of electricity produced at that point, and you can see it's most renewable in the Netherlands, and a little bit of extra low carbon. Low carbon is, for instance, nuclear, where renewable is hydro, wind, and solar. Compared to Sweden, where you have 74% renewables, and the rest is probably nuclear, because they do have a few nuclear plants in Sweden. So just moving your workload, instead of running your servers here and moving up here, you save a ton of, or a lot of CO2. The only problem is this changes over the day, so you can't really count on it being static, right? It changes all the time. You never know when, I don't know, big cloud moves over Sweden, for instance, or they run out of water. So if we try to take a look at electricity maps, let's try to do that. Let's see where the screen is. That's here. Oops. And then I need to find my mouse. So this is electricity map showing live data. I put it to live data here around the world. And if we zoom into Australia, for instance, just for the fun of it, we're in New South Wales. You can actually see here that the current carbon intensity is 438. and half of it is renewable. So I guess you got turbines and not too much sun today. But actually, you can see that here. So where is the electricity combination coming from? So it's a lot of coal and a lot of solar and a little bit of wind, a little bit of gas, and then you export it to Queensland and Victoria also at the same time. But even more interesting, if you scroll a little bit down here, you can see it over time, the last 24 hours. So you can see that the carbon intensity at night here, I've been watching the last couple of days, goes down because, of course, less electricity consumption. So I guess you charge your EV here, probably also cheaper at the same time. But during the day, from around 9 o'clock until 9 o'clock in the evening, the carbon intensity is quite high. And if we just, for the fun of it, zooms out, and goes to Europe, for instance, you can see a trend here. Like on my screen, is that Sweden is always super green compared to, for instance, Poland. So don't run a workload in Poland. So that was the carbon intensity, and they have an API. Costs a little bit of money to use. You can watch what time. I think it's free, but they have a nice API here, and the app works. I use it quite a bit. So that was electricity map. So we did time shifting. So basically we did was ask the user, all right, cool, you just submitted a job. We can, based on the data we have from electricity map, if you run it now, we know it's going to take about an hour with that many cores, CPUs and stuff like that. That will emit X amount of carbon. But if we can move it until tonight and start at 1 o'clock, Y amount, and then we can just give them, okay, you can save 18% of your carbon by, if it's okay that we submit the job and you'll be ready tomorrow morning at 8. So that was time shifting. Didn't really save us any money. We just moved the compute into another time. And then there was location shifting, where we sort of, for instance, moved to Sweden from Western Europe to Sweden Central, or from Netherlands to Sweden. Those two regions, a lot more regions we used. In my case here, what was that? 230, I think it's from the Netherlands right now versus 25 in Sweden. So just moving the workload there also is quite lowering the carbon emissions. So that's quite good. But pricing might be affected a little bit here, because the price of a product, even though it's the same virtual machine, might not be the same in all regions. Might be a little bit more expensive in Sweden, for instance. There's also a cost of moving things from one region to another, network traffic, for instance. And that cost is both monetary and carbon. But we actually, even though there was quite a bit of data here, so we had these 400,000 cores. Often we had jobs. We call it a job, where you do this simulation with up to 10, 20,000 tasks. And the input for that job was around 10, maybe 15, 20 megabytes. So it wasn't much we needed to move to another region. That was almost nothing. The only problem we had was the output. I'm going to get a little bit into that, because often that could be gigabytes, 100, 2, 3, 4, 500 gigabytes, which did incur some cost and some CO2, but it was negligible, almost nothing compared to running it in the region. So we actually didn't calculate that part as part of our calculation. We simplified that solution. All right, so how do we do this time and location shifting? Where we coordinated time, data, and all this stuff. So this is a simplified solution architecture that sort of shows how the system was built. If you look at, I'm going to do like this, because over here on the left, that's the on-premise solution, or the on-premise tool they have here. So they had a database, they had something they call a DC client, which was something they already had. We just modified it a little bit to use our API. Everything over here is in Azure. And over here, I've created two, we call them satellite region, meaning you have one here in Sweden, and this is supposed to be a cluster. So these cherries are let's say nodes, and you have also one in Western Europe, and they have a storage attached. This is just blob storage or S3 buckets or whatever you want to call it. So this is how the solution is designed. We're not going to talk about all the solutions here, there's all the things on this design, but this is how it works. So the DC client, whenever you submitted a job, had these files where you're supposed to execute these 10, 15, 20, 25 megabytes of stuff, an executable, for instance, instructions, configurations, and all kind of things. That was submitted through the DC client and copied over to the artifact storage. The artifact storage is a file share, nothing fancy. And then the job was submitted to the API. The API didn't do much. It asked you whether or not it did the calculation. I actually not drawn it up here. It did the calculation, figuring out, what if I run it later today? How much less CO2 could we save? But otherwise, it just validated. Okay, cool. You say there is a bat dot or a executable dot something in the file. Yes, it exists. Does all the whatever things were there, an authentication and stuff like that. We updated our state store here in the bottom, and up here we added a message to the queue. So okay, start processing. If we knew that it was going to be processed later, we actually delayed that message or actually put it onto the queue and say, pop up in 4 hours. Otherwise, that was a simple way of doing it. Then we had the dispatcher. The dispatcher is where all the core business logic was sort of working. And that was suddenly becoming a little bit more complex when we did this location shifting. Because if we pick up that message from the queue and say, okay, I want to process this, we needed to figure out how long it would take, how many resources it would require, and stuff like that. So we started going to the artifact store. That's the error there, and figuring out, okay, cool. There's 20,000 tasks. It's going to take 100,000 CPU hours or whatever it is. If we spin up 1,000, it's going to take 100 hours. That was my math there. That's pretty good. 100 hours to actually process this entire job. So what we did here is that we queried we call it, in this diagram, it's called the cost and CO2 API. It's a little bit simplified, but we queried the cost API is Azure pricing API, that's public pricing API, to figure out, okay, what's the difference price between running 1,000 VMs in West Europe versus Sweden Central? That was the difference in price. And also, what can we get of spot instances? And then we called the CO2 API, that's electricity map underneath, to figure out, okay, where's the best location? And then at some point we figure out, okay, the best location is actually running it in Sweden Central. And then we copied the files over there because we don't want 10,000 or 1,000 VMs to start copying over network somewhere. So we could just copy the input files over here, and each of the nodes actually picked up the input files and read them. If we couldn't get the number of cores available, or the cluster is scaling or something, then we just put the message back in the queue and put a little delay on it, for instance, a minute, and then we try it again. Okay, cool, now we got the cluster we wanted to have. We're trying to run everything on spot instances. We might not be that lucky, but that's what we did. And then we might reevaluate and figure out, okay, we can't get it to Sweden, we need to move it to Norway, to West Europe. The output was a challenge of us because a couple of 100 gigabytes, even though there is fiber thick connection, actually takes a while to copy. So we knew, we were lucky, we could figure out when a job was, or a task is done. And then the task would dump some files in that output folder. So whenever something landed in the output folder, we knew it was done, completed. So we used Event Grid to monitor whenever something lands in a storage account. And as soon as we got a file there, we've got an Event Grid notification that picked it up, executed by the blob trigger Azure function, picked it up and started copying it right away. So we had massive parallel copying of data back, and so we got it back to the users as quickly as possible. Otherwise, it could easily take hours to actually copy the data back if they were a really large job. We used a lot of other things, App Inside, Grafana, DevOps. We had something called Cloudburst Monitor. I'll actually show you that in a second also. Yeah, so time and location shifting. If we did time shifting within a day, like we couldn't get a forecast very, very precise more than 24 hours into the future. We actually managed to reduce the carbon emissions of just by time shifting, delaying things to 12 to 16%. That was the reduction in carbon emissions. But location shifting within the EU, that was a requirement. We're not allowed to move outside the EU. We could easily get 30, but sometimes up to 90% reduction in carbon emissions. That's a huge number. But that was also the most complex part of the solution, building that, because we needed to be able to spin up clusters in multiple regions. All right. So the tools we built all this stuff with, most of it is actually from Green Software Foundation, which I mentioned earlier. And we actually contributed back some of the tools also to the Green Software Foundation. So Green Software Foundation, besides having these principles, also has a way to measure. How do you measure software emissions? How do you do that? And they come up with something they call software carbon intensity. And when you see the formula, it's deceivingly simple, or actually it's a little bit complex. So before showing you the actual how you calculate, I'm going to walk you through an example. I've just taken a random server, which is fairly used. It's a Dell PowerEdge 3 gigahertz AMD processor with 16 gigabytes of RAM, and want to calculate what's the software carbon intensity of this server. So it's a 400 watt server. And, I want to calculate it in 1 hour. Let's say from 2 to 3 today, or 3 to 4 today. So it's a 400 watt server. Assuming it always uses 400 watt, it doesn't. I'm going to simplify the calculation a little bit here. It's 0.4 kilowatts hour. And then there's something called embodied carbon. That's one of these weird terms. But embodied carbon of the server means the amount of carbon required to produce all the components inside the server, ship it to wherever you want it, and at one point decommission it. So a Dell PowerEdge is probably around 1,000 kilos. Actually, I couldn't get the numbers. I tried to reach out to Dell, so I guesstimated it based on other stuff, but Dell couldn't provide the values to me. So the embodied carbon for a server, let's say it has a 4-year lifespan, is 1,000 kilo divided by 4 years, 365 times 24, which yields 28 grams per hour. And then we have the carbon intensity. That's where we use electricity map, just checking a random number, 216. So right now, we assume that the carbon intensity is 216 here in New South Wales. And then we need a functional unit. I get into that a little bit, but you need something to calculate it on. So I've, in my mind, come up with a web shop. So in that web shop, we got 398 orders in that hour. So that's the way of sort of quantifying the calculations. So, and again, simplified super, there's no cooling here, there's no networks, there's no anything like that. That's just the server. Otherwise it becomes super complex, but you can easily add those if you want to. So this is the formula. And it's actually quite clever. So the software carbon intensity consists of energy consumed by the software. That's the 400 watt. You can plug in a meter in front of your server, and then you'll know the actual value if you want to get that there. It's the carbon emitted by producing of electricity, meaning the carbon intensity, 216. It's the embedded carbon or embodied carbon producing the server, and it's the functional unit. In my case, it's the orders processed on this web shop, but it could be a number of messages processed through your system or similar. So if we take the values here and put them into the formula, it's too much clicking here, 0.4 times 216 yields 86 grams for operating this server, 86 grams of carbon equivalents, plus the 28 gives us 114, divided by the number of orders gives us an average of 0.31 carbon dioxide equivalents per order. So if you can optimize any of these values here, if you can lower the energy consumed by, I don't know, replacing the AMD processor with ARM processor, you can lower the E. If you, I don't know, erect your own turbine, you can lower the I. If you extend the lifetime of your server for 4 to 5 years, you can lower the M. And if you, I don't know, get more customers, that's easier said than done. But make your system more efficient. If there's messaging processes, you can increase the R and then sort of get these values out. I mentioned it was impossible for me to get these values from Dell. It's not easier from Microsoft. I do have some of the numbers, but they're not public. They are getting there and fighting heavily internally to sort of get these values out. But, so I have no clue how much energy a server produces consumes in Azure. I know the carbon intensity because I know where the regions are. I don't know how long they're going to keep the servers. I don't know anything about the servers in reality. I just know it's a machine underneath. But I do know this one. But I was lucky in my case because, because it's the same server with the same lifetime span, and it uses the same electricity. It doesn't matter whether or not it's running down in a region, Azure region in Australia, Sweden Central, or Western Europe. So I could actually ignore the E and M when I did this calculation because I could just compare those two. Hence, I ended up almost only with the I, the carbon intensity. And that was actually what we mostly looked at when we did these calculations. So if you want to do something similar, pressure Microsoft to release some of these numbers. They are getting there, and they're a little bit slow. But I haven't found anybody else releasing them either, but somebody has to be the first. We used the Carbon Aware SDK to actually do quite a bit of this. This is an open source library from Green Software Foundation, and it has a nice API. It's also CLI, it's DLL, it's everything. We actually contributed quite a bit to it, and it's actually run by an Australian, Vaughan. I think he lives in Sydney, actually. And it has some nice APIs. For instance, one of them we used is we knew how long this workload was going to take. We knew we want to run in either Sweden Central or Western Europe. And we knew we wanted to be done by no later than 8 a.m. the next morning. Hence, we could just ask this API, when should we run? The Carbon Aware SDK just pulls a data source underneath, for instance, electricity map or what time. Electricity map, the one I showed. So that was fairly easy to use. We actually use it internally at Microsoft. So this project has carried a lot of things inside Microsoft, so I'm really pleased about that. But Vestas also provided yet another challenge for us, which I didn't see coming, because right now the system was super intelligent. It always picked the best region of, the region with the low carbon intensity. But there's nothing that sort of controlled cost. And the Carbon Aware SDK did not do that either. So I assume most of you wouldn't mind paying 5% extra for, let's say, a 50% carbon reduction. That's probably why some of you have an EV. But if you reverse that statement and saying, will you pay 50% extra for something, car, you probably already do, but only get a 5% reduction in carbon emissions, not many businesses would see that as a viable business plan, sort of doing it. And Vestas did the same thing to us. Yeah, sure, we really want to stay the most sustainable energy company in the world, but we don't have unlimited funds. Fix that problem for us too. So what we did, we created Carbon Economy SDK, which we are contributing back to Carbon Aware, to the Green Software Foundation. It just takes a while for them to sort of accumulate it. So how it actually worked, it was super, super simple. It's not many lines of code, to be honest. So we had the dispatcher, and I just talked about the carbon aware SDK, and I talked about the pricing API. But that's what the carbon economy SDK did. So the carbon economy SDK called out to get the recent prices of services in Azure. They don't change that much, but we don't know about the future, whether or not there's going to be daily prices or whatever it is. Right now, they change, I don't know, once a year or so. We got the prices for both the VMs we wanted and the spot instances. And then we called the Carbon Aware SDK. Okay, when is the right time? Blah, blah, blah. The API you saw before. And it called out to electricity map. And then we had a super advanced calculation here in the middle. No, not really. We actually spent quite a bit of time trying to figure out how do we create this formula. And this was what we ended up with because it works really well. So it's a normalized calculation of the weight, where we have a weight, how green you want to be, versus how cost conscious you are, and did this calculation. I think we spent 3 months trying to come up with, and we ended up with this simple one. You should see some of the other alternatives. They were hugely complex. Nobody understood them. This is fairly straightforward. And if you look at the calculation, there's two examples here. There's upper table and the lower table, where you have emission weight. So you're fairly interested in low emissions. So it's 0.25, and you have a emission weight later in the lower table, which is 0.75, meaning you're more cost conscious. So the calculation here is that we just took the numbers are the same for the emission rating or carbon intensity and the unit price. These are not actual values. It's just used to show the point. So even though Sweden Central is the greenest region right now, compared to West Europe, for instance, there's a price difference. Hence, when we do the calculation, we end up figuring out that we should definitely not be in Sweden Central, but we want to be in West Europe. And actually, we could prioritize, and that's what we did too. So if we couldn't get the resources we wanted in Western Europe, we can go to next worst or next best, or whatever you want to call it, which is UK South, for instance. But if you change the weight with the same values, you see you end up in Norway East, which is another Azure region, and the worst situation is UK South. So super simple calculation. And then we also created, we had a designer help us create a UI to sort of make this a little bit intuitive. And the first thing she came up with, or actually did some really clever, was this part. So this part was where the users can, or the admin can choose how cost conscious, how environmentally they are at this point. You got to remember, an admin is not the end user that sort of submits the job that makes these decisions. There's somebody with a budget, and they might have a carbon budget. They might have, which they actually do inside Vestas, but they also have a monetary budget. So they could sort of move these sliders left or right. And of course, the leaves represent the greenness, and the dollars bills represent how much money you're willing to spend. And we nudge the user a little bit. So if you look at this one, if you move the sliders a little bit, initially it's defaulted to very green. But if you move the slider a little bit, it becomes less green. And eventually, if you're cheap, it ends up like a cesspool. There was actually 25 images, but I don't want to show all of them. But there's 25 settings we sort of created. Besides that, we had we gathered all the data. The forecasted carbon emission, the actual carbon emissions, when a job was run, when it was run, if there was any delay, all kind of stuff. So we created these trend graphs saying, okay, your carbon reduction is your carbon reduction increased in this case, and the budget spending. We had all these kind of information. We knew how much money they were spending also every month, and other settings here. And then we added up a small nudging section up here. You don't have to read what it says up there, but as we had all these values, we could also calculate and saying, the last 30 days, if you move that slider one notch, and you want to be a little more green or use a little bit more money, that would have resulted in, let's say, 18% carbon reduction, and it would only have cost you $1,000. And that works really well. To be honest, initially when we started this solution, all these sliders were in the middle, and it took quite a while to get each department to sort of change them a little bit. So the default was changed to greenest, and then they'll figure out whether or not they spent too much money. Cool. That was Vestas. That's how we built the solution. There's a blog post. I'll share that later if you want more details of how we make all this make possible. There's also a couple of videos online about what we did with .NET and stuff like that. But Microsoft is getting into this game a little bit. So about a year ago, CADA is a scalar job processor in AKS, or actually in Kubernetes, not AKS, where you sort of have a simple implementation of what we did here of time shifting. So you can sort of say, okay, when you start processing, how many replicas do you want depending on the carbon intensity? And that uses the Carbonware SDK and connects, for instance, to electricity map or what time. So that's an initial one. And last week, something more came out. So I actually public preview. I think it was actually this week, sorry, not last week. This came out. This is inside the Azure portal. Now you now have access to a blade called Carbon Optimization, where you sort of, sorry about the resolution. I can see that's terrible, but you can see the total amount of emissions for your subscription. And you can see the monthly breakdown, and you can see reduction recommendation. Unfortunately, you can only do it at subscription level, and it doesn't work for all resources yet. I'm pushing them heavily. What I would like to see in the Azure portal is whenever you see a price, I want a disk, whatever, $2 an hour. I don't know, 400 grams of carbon emission, whatever the value is. And then when you build your system, you'll get everything in there. That's the first one. That's for reporting. But what we did with Vestas was sort of, we took action on it, right? So based on data we got from electricity map through Carbon Aware SDK, we sort of move workload around. The next step I would see whenever we're done with this, getting this into detail, is actually having our Azure's managed services do the same. Right? If you have something that's batch oriented, cron jobs or whatever, why not have the solution do it automatically? I don't want all of you, I don't want to build this multiple times, but do push your Microsoft representative, or Google, doesn't really matter, or AWS. As long as we get there, if one of them starts, the other one will follow quite quickly. I have a link down here to a detailed blog post, what's happening. But I am super passionate about this, about carbon intensities and supercarbon, how do we lower this? And I'm really proud of what we did with Vestas. It's sort of like, in my mind, it's sort of like Inception. Like we built this turbine simulator to make the turbines even more efficient, use less resources, and generate more electricity, renewable electricity. And then we built a software solution on top to do these simulations that sort of try to figure out how can we do this without consuming too much, or emitting too much carbon intensity. I have a lot more I can tell you, but I wanted to give you 5 minutes for questions if you have any, or otherwise you're of course welcome to come up and discuss, and I can share even more. And most of the source code is actually public also. It's not that super interesting. The most interesting part is Carbon Aware SDK and Economy SDK. The rest is boilerplate. So, thank you very much. Do you have a question?
I was just curious as to how long it took you to build the solution.
So how long it took to build the entire solution? It took us 8 months. But there was a lot of hurdles. We needed to understand what they were running, because that was super complex. I don't get it still, to be honest. and we invented things while we built it. Like I mentioned, the financial bit, the carbon economy SDK, they just came with that problem at one point. They said, yeah, this is awesome. I haven't even thought about it. Right? I was just blinded by, I can lower the carbon emissions. And we were fighting internally to try to get some of the, I could get some of these carbon emission numbers, but I couldn't share them. Like the PUE of the data center, I know the PUE of the data center, and I could give them to Vestas, but I can't share in public. So it was a little bit of a challenge getting all that stuff running. But we were a small team, and it took us 8 months or so. Any other questions? Yes, the Carbonara SDK is used by multiple companies. I know UBS, Microsoft, and Vaughn will actually be here tonight, so you can ask him. He's the lead of the. I asked him to come, so he'll show. Probably, I don't know. I know they track a list on the Carbonara SDK, the Green Software Foundation homepage, but yeah, that's great. No, it's not specific to Azure at all. So it's written in .NET, but it's delivered as a, and that's not my decision. It's delivered as either a Docker image or anything like that. And the value of the Carbonware SDK is it makes using these electricity map or what time APIs super simple. Sort of does some aggregation on top. Otherwise, you'll just get this. So the way that this data actually works is that every 15 minutes you get a value. And there's also something about how accurate it is when you talk about the future. And it normalizes all that for you. And you just ask for a period of time. That's why we use the Carbonware SDK. We did consider doing it ourselves, but once we started looking at the API, I was like, no thanks. I might as well just add another DLL or a process that does all this pre-computation for us, which was super easy to use. Did that answer your question? Okay. Cool. Thank you.